This is the 13th video in our series on Lie algebras, and today we're going to talk about a certain bilinear form of a Lie algebra known as the killing form. But in order to do that, or before we do that, we're going to recall a couple of things. Like, let's recall, if you have a Lie algebra L, its derived subalgebra, which is denoted by L prime, is equal to the bracket of L with itself. So let's recall that is the span of the bracket of X with Y, where X and Y both come from L. And I think earlier we worked with this quite a bit and we generalized it maybe to, bigger things. Okay. And then from there, you can inductively define Ln plus 1 as the bracket of L upper n with itself. In other words, it's the derived subalgebra of the subalgebra L upper n. Then let's recall that L is called solvable if there exists a natural number n so that L upper n is equal to 0. But of course, that means that L upper little n is equal to 0 whenever that little n is bigger than or equal to the capital N. So it like truncates that series of the L upper index. And then we have another definition which says L is semi-simple if its only solvable ideal is the trivial ideal. In other words, the ideal containing only the zero vector. But let's also recall that the radical of a Lie algebra is the largest solvable ideal. So this is equivalent to saying that the radical of L is equal to the trivial ideal. Okay, now finally to our definition for the day, or at least the one we're going to start off with, and that is the killing form. And so we'll denote it by this kappa, and it has two inputs, both from L, and one output from, well, this should be from the ground field, which we're taking to be the complex numbers. And what it does is it takes x, y, and sends them to the trace of add x times add y, where add x and add y can be represented by matrices. And this may seem a little bit nebulous just looking at the definition, but via some examples, it's not too bad. So let's look at our favorite toy example, which is maybe the most important Lie algebra to understand, SL2. So it's three-dimensional, spanned by vectors E, F, and H, and we have the following bracket relations. So let's note that if we have add H, so acting on E, we'll get, well, that's defined to be the bracket of H with E, or 2E. And then if we have add H acting on F, well, like before, that is defined to be the bracket of H with F, which is minus 2F. And then finally, the adjoint action of H on itself will give us the bracket of H with itself, which is 0, just by the skew symmetry or the anti-commutativity of the bracket. But now if we think to ourselves of, let's see, E being, maybe what order should we do this in? Maybe let's say that H is the column vector 1, 0, 0, E is the column vector 0, 1, 0, and then F is the column vector 0, 0, 1, then this action of the adjoint action of H tells us that in this basis we have add H, maybe I'll say that the basis is HEF, is represented by the matrix 0, and then let's see, 2 on that part of the diagonal, and then minus 2 on that part of the diagonal. And that's simply because, well, it maps H to the 0 vector, it maps E to 2E, and it maps F to minus 2F. Okay, so there we have it. There is add H represented in this basis. But the important thing here is that the killing form is invariant, or maybe taking the trace, I should say, is invariant of choice of basis. That's what makes this well defined. If the trace depended on whatever basis you were working in, well, then this wouldn't be a good definition. But needless to say, the trace is independent of basis. So, we can do this representation just because it's easy, if you will. Okay, so let's observe that that means the killing form of H with itself is going to be equal to the trace of this matrix, 0, 0, and then all of these zeros, and then a 2, and then a minus 2 squared, because we're simply multiplying that matrix to itself. But let's observe that that's equal to, let's see, the trace of the diagonal matrix with 0, 4, 4 on the diagonal. Of course, we're using the fact here that minus 2 times minus 2 is positive 4. So here we get 8 because 4 plus 4 is 8. So the killing form of H with itself is equal to 8. Now let's maybe find another one of these. So let's look at add E acting on H and observe that that's going to be the bracket of E with H. But in turn, that's going to be equal to minus the bracket of H with E by skew symmetry or by anti-commutativity, which is minus 2 times E. And then if we look at add E on E, well, that's going to be the bracket of E with itself, which clearly gives us 0. And then finally, add E on F is going to give us the bracket of E with F, which is equal to H. But then using this same kind of thing that we did above, we can represent this map add E inside of this basis by the following matrix. So let's see, it'll be 0, minus 2, 0, 0, 0, 0, and then let's see, we have 1, 0, 0 here. Okay, nice. So there we have add E represented in this basis, and that's simply because it takes H to minus 2E, that's described by this column. Takes E to 0, that's described by the second column, and then finally it takes F to H, that's described by the third column. And then similarly, we can find a basis representation or a matrix representation of add F. And I won't go through the very, very, very similar calculation, but it looks like this. So we have 0, 0, 0, 2 in the first column. And then next we have minus 1, 0, 0, and then finally 0, 0, 0. But now we can find the killing form on EF. And then that's simply going to be equal to the trace of the product of these two matrices. But if you take the product of these two matrices, you in fact get a diagonal matrix with 2, 2, 0 on the diagonal. I won't go through the calculation, but that's what you get. And that pretty clearly gives you the number 4. Okay, so we've calculated a couple of examples here. Of course, you could calculate more of these if you wanted to, but I'll leave that to you. Okay, so let's see where we go from here. So killing forms are defined on Lie algebras, so we should probably have some sort of result of how the killing form interacts with the bracket. And well, here's just exactly one of those results. It says kappa of the bracket of x with y and z is equal to kappa of x and the bracket of y with z. So it's pretty cool. You can just slide this bracket from one entry to the other. I mean, that's what it looks like. That obviously that's not exactly what's happening. Okay, so this is a pretty straightforward calculation where we simply use the definition of this killing form along with some things that we've proven in the past. So here we'll have that this is equal to the trace of add of bracket xy times add of z. Okay, nice. But like I said, in the past, we talked about what the adjoint action of a bracket looked like, and in fact, looked like the bracket of adjoint actions. And so we'll use that here. So this is from a previous result that we get the trace of add x, add y, minus add y, add x, all times add z. And now we can write the bracket of the adjoint actions in terms of a commutator like this, because when you're talking about the adjoint action, you're talking about a linear transformation, and the commutator turns into, or sorry, the bracket turns into a commutator in that case. You're really talking about multiplying matrices in some sense. But now what we're going to do is add a version of 0 and rewrite this in, well, the form that we want it. So let's get it written down and then we'll see how this works. So this is the same as the trace of add x times add y, add z, minus add z, add y. And then after that, we have minus add y, add x, add z, and then plus add x, add z, add y. Okay, nice. So let's see what term we added and subtracted. So we naturally have a term in the order of x, y, z, from this term multiplying onto this term. So we see that from the distribution of add x onto this first term. And then we also naturally have one in the order y, x, z. So what we've done is we have subtracted this term and then added it back in. So that's our adding of 0. And then the other stuff comes from above. Okay, nice. But now we can rewrite this as the trace of, but next up we can break this into pieces. So the trace is an additive function. I think that's pretty obvious. So we can pull apart this part, which is pretty clearly equal to the killing form on x, comma, the bracket of y with z, simply reversing some of the steps that we had above. And then after that, we'll have this is plus the trace of, let's see, it'll be the bracket of add x, add z with add y. So that actually can't be written in terms of the killing form, that second term, but the important thing here is it's the trace of a pure commutator. Yikes. But we've proven before that the trace of a pure commutator is always equal to 0. I won't go through that, but because we've done that before. And we're kind of getting to the point in these videos where we have to rely on previous results. Otherwise, we just dig ourselves into a hole every time of reproving old results. So anyway, let's look at this left-hand side and the right-hand side and see that we have achieved exactly what we wanted. Okay, so now let's move on from there. So now moving on, we need to recall the Jordan decomposition of a linear map. So let's say we're given a finite dimensional complex vector space V. So we don't really need it to be complex, we need it to be algebraically closed or over an algebraically closed field. But it's just most reasonable to choose the complex numbers. Okay, so we've got our vector space over C. And then we also have a linear transformation, which we'll call T from V to itself. Let's recall that we might say that T is an element of the endomorphisms of V, and write it like this. So given that setup, we can uniquely write T as T sub D plus T sub N, where T sub D is diagonalizable and T sub N is nilpotent. Now this is like very connected to the Jordan canonical form of a matrix, or really a linear operator. And that says that there is a basis B of the vector space V, so that in that basis, this linear operator or linear transformation is represented by this block diagonal matrix. So I've put on the diagonal these j lambda 1 through j lambda n, and these j lambda i's are called Jordan blocks. And what you have here is on the diagonal, you've got lambda I, and then just above the diagonal, you have a bunch of 1s, and then everywhere else you have 0. So now we can clearly see what the diagonalizable part is and what the nilpotent part is. So the diagonal part will just be all of these lambda i's, and the nilpotent part will just be all of these ones that are above the lambda i's. And I should say that in this setup, the lambda i's are called generalized eigenvalues. And then you've got generalized eigenvectors connected to them as well. Okay, so here's the next lemma. And that says, if we've got one of these linear transformations, and we've decomposed it using Jordan decomposition, then we can find a polynomial p with coefficients in the complex numbers so that when we evaluate our linear transformation at the polynomial, we get the diagonal part. Okay, so let's go for it. So let's let lambda 1 through lambda n be the eigenvalues. And I guess I should have said that over here, these lambdas are actual eigenvalues. It just turns out that you get, at least one eigenvector for each of them, but you might get a bunch of generalized eigenvectors as well. It's kind of depending on the difference between the geometric dimension and the algebraic dimension of the eigenspace. Okay, so anyway. So now let's let lambda 1 through lambda n be the eigenvalues of t, and then let's decompose our vector space. So we'll decompose V as, I'll write this as V1 direct sum V2 all the way up to the direct sum of Vm. Oh, and I should say that this ends at m. And then, like I said before, like I kind of alluded to, this Vi is the generalized eigenspace of lambda I. Okay, so what does that mean? Well, that means that if we take T minus lambda I times the identity matrix and raise it to the power the dimension of Vi, and then we restrict that to Vi, we get the zero vector. Okay, or we get the zero linear map, I should say. So vectors that get killed by this operator here are exactly these Vi. So that's sort of the setup that we're going on here. Okay, so next up, we want to use the Chinese remainder theorem on C adjoin T. So you might know the Chinese remainder theorem from a number theory class, but it holds in a more general world of rings than just integers modulo m and n. Okay, so this allows us to find some polynomial p of t in C adjoin t such that we have p of t is congruent to lambda I modulo t minus lambda I to the power dimension of Vi. Where when I say mod that, it looks like I'm saying mod a polynomial, but really it's mod an ideal generated by that polynomial. So let's see, this is equivalent to saying the following, and that is that p of t minus lambda I, well, is an element of this ideal. So in other words, it's equal to q sub I times t minus lambda I to the dimension of Vi. So recall, in order to be in an ideal generated by a single element, you are a multiple of that single element. And these q's, that's just a polynomial to make it happen. So next up, we want to take a vector v in Vi and observe the following. So observe that if we take P, evaluated our linear transformation, and hit it on V, what will we get? Well, we're going to get lambda I times V. We're going to get lambda I times the identity matrix minus Qi of t times t minus lambda I, all raised to the dimension of Vi, and this is all multiplying into V. So simply what I did here is I solved this equation right here for P of t, and that's what I replaced this P of t with. But now observe that this second half of this expansion multiplying into v will give us 0. And that's because v is in vi. And, well, this object right here is the 0 map on vi. So, needless to say, all of this stuff just disappears. Then we have lambda I times the identity map on v. In other words, we'll just have lambda I times v. But what does that tell us? Well, that tells us that on vi, we have P of t looks like simply the diagonal matrix with a bunch of lambda i's. But then if we just glue all of these vi's together, well, we'll have a diagonal form for the expansion of this polynomial, and that diagonal form is exactly the diagonal form kind of described down here by the Jordan canonical form. In other words, that gives us P evaluated at t is equal to TD as needed. Okay, so now let's move on to maybe kind of the big result for today. Okay, so our first big result today is called Cartan's criterion for solvability. And we'll start with a complex Lie algebra L, and we'll prove that L is solvable if and only if, for all x, y, z in L, we have kappa of the bracket of x with y and z is equal to 0. Okay, so let's get to it. So this forward direction, we want to suppose that L is solvable. Okay, and then from there, we'll use Lie's theorem. So if you recall from several videos back, we had, let's see, Lie's theorem and Ingles' theorem, which described when Lie algebras were solvable or nilpotent. So we'll use Lie's theorem to find a basis for L so that I'll call them W in L, add W is upper triangular. So I think like the big takeaway from Lie's theorem was that solvable Lie algebras was like a abstraction of Lie algebras of upper triangular matrices. So that's like essentially what we're using here. Okay, but now from there we see that the bracket of add x with add y is strictly upper triangular. So the thing here that we're using is that if you take two upper triangular matrices and you take their commutator, you get a strictly upper triangular matrix. And then furthermore, if you multiply by another matrix, you still get a strictly upper triangular matrix. So in other words, if we take add x, add y, and we multiply that into add z, we also get a strictly upper triangular matrix. Okay, so just to reiterate, add x and add y are both upper triangular. We bracket them, we'll get a strictly upper triangular matrix. We proved that, or we used that before. That's easy to see with some calculations. Then if you take a strictly upper triangular matrix and an upper triangular matrix and you multiply them, you get a strictly upper triangular matrix. Now let's use one of our results from before that allows us to write this as that bracket, or the add of the bracket of x with y times add z. But next up, let's take the trace of that. So if we take the trace of this, it's the same thing as taking the trace of the line just above. But the trace of a strictly upper triangular matrix is simply the sum of a bunch of zeros, which is 0. So we get 0 there. But then this trace right here is exactly the definition of the killing form on the bracket of x with y with z. So we have our necessary killing form is equal to 0, finishing this forward direction. Now moving on to the reverse direction. So we'll suppose that all of this holds. So suppose for all x, y, z in our Lie algebra L, we have this killing form on the bracket of x with y and z is equal to 0. And then here's in fact what we'll show. So we will show the following, that if L prime, which let's recall that that is the derived subalgebra of L, is nilpotent, then that implies that L is solvable. So if we can prove this, then all we need to do is look at L prime and show that it is nilpotent. Okay, so let's observe that if we take a W, which is equal to the bracket of x with y inside of L prime, then we know that kappa of W with Z is equal to 0. That's just by the given. Now what we'll do is take W and take its adjoint map and write that adjoint map as a decomposed version with its diagonal part as well as its nilpotent part. So recall that W itself may not be a linear transformation, but its adjoint action or its adjoint map is a linear transformation from L to itself. And then just to keep things a little nicer here, I'm going to rewrite this as capital W sub D plus capital W sub N, just so I don't have to rewrite all that adjoint action stuff every time. And now let's note the following. If we take the trace of W times the conjugate of WD, what we'll get is the trace of WD times WD bar. So I think that's pretty clear just by the way that W will multiply into, well, essentially its diagonal version just with the complex conjugate. But then we can pretty easily see here that we're multiplying a matrix with all of the eigenvalues of W, and here all of the conjugates of the eigenvalues of W. But that'll give us the modulus squared sum of all of the eigenvalues of W. In other words, we have lambda 1 squared plus all the way up to lambda m squared, where, just for completion, lambda I, these are eigenvalues of our capital W, which recall was add little w. But now let's also work this trace in another direction. So on the one hand, we know that it's that sum, but then on the other hand, we can write it as the trace of, let's see, add W, which, I should point out was add of the bracket of x with y from our definition of W here, and then times this add W bar where we've taken the diagonal part. Now we can use a property of the trace as well as the commutator to rewrite this as the trace of the adjoint action of x with the adjoint action of the bracket of y with W bar where we take just the diagonal part. Okay, great. But then by our earlier trace relationship, we know that this trace has to be equal to 0. So let's bridge the gap right here. We have this sum of, those are going to be non-negative real numbers and they sum to 0. So that means that they are all in fact equal to 0. That's the only way that you can sum non-zero real or non-negative real numbers and get zeros, for them all to be 0. But what that means is that add of W is simply equal to this W sub n. It's all its nilpotent part. But then let's look at this. W came from inside of L prime. So that means that L prime is nilpotent, because we showed that an arbitrary object inside of L prime was nilpotent, so that makes the whole thing nilpotent. But then by Engel's theorem, which we proved much earlier, that implies that L is solvable. Okay, so I know I said this was the first of our big results here, but I think we're gonna save Cartan's other criterion, the criterion for semi-simplicity, for the next video, as we've kind of gone over a lot today. And we'll include the exercises for both of those videos at the end of that video. And that's a good place to stop.